All right, let's dive right in. Today, we are going to tackle one of the biggest, most fundamental concepts we all just take for granted, time itself. Get ready, because we're about to take apart everything you thought you knew and then rebuild it from the ground up, all based on the pretty fascinating work of physicist Miles Mathis. So let's just kick things off with the big question. Is time really this river we're all floating down, a fourth dimension that's woven into the very fabric of reality? Or, and this is the big one, what if we've been thinking about it completely wrong this whole time? So here's how we're going to break this all down. We're going to start with a pretty radical new definition. Then we'll look at what our clocks are actually doing. We're even going to rewrite a basic physics formula, poke around at one of Einstein's core ideas, and challenge this whole notion of four-dimensional space. And it's all going to lead us to a completely new way of looking at time.
Okay, let's get right to the heart of it. This entire argument, everything we're about to unpack, it all hinges on one simple, powerful, and honestly, pretty provocative idea.
That's it. You heard that right. The core idea is that time isn't its own thing. It's not some mystical dimension. It's just a yardstick we invented to measure motion. So whenever we think we're measuring time, what we're actually doing is measuring movement. And if you think about it, without movement, the whole concept of time just kind of disappears.
Well, that naturally leads to a pretty crucial question. If time is just a way to measure movement, then what in the world are our clocks doing? I mean, what are these super precise instruments we've built really tracking? Let's take a closer look.
This question really forces us to look past the digital display or the ticking hands and to ask what's fundamentally happening inside any kind of clock. And this is just brilliant, because it makes the point so clearly. Think about it for a second. A pendulum clock, it's measuring the distance of a swing. A super fancy atomic clock, it's measuring the vibrations of a cesium atom. And hey, even our most ancient clock, the sun, marks time by its movement across the sky. Every single clock we've ever invented is just a device that measures a physical, tangible movement.
So this all leads us to what's called an operational definition of time. Basically, it pushes aside all the philosophy, what time feels like, and it just focuses on what we're physically doing when we measure it. And what we're doing is simply comparing one movement to another.
Now, what's so interesting here is the contrast. We're so used to thinking of time as this abstract, mysterious dimension that we're all traveling through, right? But this operational view says, nope. It treats time as something totally concrete and physical. It's just a direct comparison of two movements, where we've decided to call one of them our standard, our clock.
Okay, you might want to hang on to your hats for this next part, because if we accept this operational definition of time, it has a staggering implication for one of the first equations we all learn in physics class.
We have all seen this 1,000 times. Velocity is just the distance something travels divided by the time it took to get there. Simple, right? But if our new definition is correct, this equation is hiding something massive in plain sight.
Seriously, think about this. If for time is really just a measurement of a clock's internal movement, which is a form of distance, then what we're really doing when we calculate velocity is comparing one distance to another distance. It's the distance the object moved divided by the distance the parts of the clock moved. It's distance over distance.
And here's the quote straight from the source. Velocity isn't distance over some abstract thing called time. It's just a ratio of two distances. You're comparing the unknown movement of some object to the known, standardized movement of your clock. That's what velocity really is.
Okay, I know what a lot of you are probably thinking right now. But what about Einstein? Doesn't special relativity, with time dilation and space-time, just blow this whole idea up? Well, according to the source material, Einstein's theory actually depends on this very idea.
Let's go back to basics for a second. What was the foundational rule of special relativity? It was that the speed of light in a vacuum is the same for all observers, no matter how they're moving. That was Einstein's non-negotiable starting point.
Now here is the key insight. If you say that light travels at 300,000 kilometers per second for someone on Earth, and for someone on a super-fast spaceship, you are fundamentally assuming that the relationship between their local kilometer and their local second is the same. Their own personal clocks and their own personal rulers have to be equivalent for that constant speed to mean anything to them.
And the argument is that even a giant like Richard Feynman understood this.
You can't even begin to do the math to connect different reference frames, different systems, unless you start by assuming that their local measurements of time are fundamentally equivalent, even if they might look different to an outside observer.
So, if time is just a measurement of movement happening in 3D space, what does that do to the incredibly popular idea of a four-dimensional space-time? This is where the argument really starts to challenge our modern picture of the universe.
Let's just break this down step by step. First, we've established time measures movement. Got it? Second, any physical movement already has a direction, a vector, as physicists call it, in our normal, everyday 3D space. So here's the problem. You can't then turn around and claim time is a separate fourth direction that's at a right angle to the other three. The math just completely falls apart. You can't divide two vectors that are totally perpendicular and get a meaningful velocity. The argument is that 4D space, while it sounds cool and is elegant on paper, just doesn't hold up physically.
So where does all this leave us? Is time absolute, like Newton thought, or is it relative, like Einstein proved? Well, according to this revaluation, the answer is kind of weirdly both. It just depends entirely on what you mean.
This table sums up the nuance perfectly. For the math to work, we have to assume that time is absolute in the sense that a second for me is equivalent to a second for you in our own local systems. But it's also relative because, let's be honest, we can never know if any clock is perfectly, absolutely uniform. And it's definitely relative in the Einstein sense. Time dilation is a real observable fact. No one's denying that.
So, if you're going to remember just one thing from this entire explainer, let it be the shift in how we think about it. Time is not some external, flowing river that's carrying us along. It's a tool. It's a ruler that we use to measure it, compare the motion of everything else in the universe.
And I really want to leave you with this final thought-provoking question. If time isn't a substance or a dimension, but it's simply a measurement of motion, what does it really mean when we say we're running out of time? What are we really losing? Something to ponder. Thanks so much for joining me.